everyone, and welcome to another CAD seminar session. Today we are very happy to have Professor Jorge Pais. He is an associate professor at the University of Minho's Department of Civil Engineering. His research areas include pavement materials design and characterization, advanced laboratory testing, field performance evaluation, and maintenance and rehabilitation techniques. He received his doctorate from University of Minho and bachelor's and master's degrees from University of Porto, all in civil engineering. Everyone, please join me in welcoming Professor.
Okay, thank you. Hi, everyone. Good afternoon. Hope you are fine and doing well and away from COVID. First of all, let me thank you for the organization, for inviting me to participate in this prestigious series of lecture. It's a honor for me to talk in Kent seminar series. My talk is about the pavement design. That is my research topic here in the University of Minho, where at this moment I'm a associate professor and where I work for 30 years doing research on pavement design, road materials, and all the subjects mainly related with pavement design. Because to talk about pavement design is not easy, because pavement design is a topic of a very large, broad spectrum. My talk intends to make an overview or a brief overview of the past, present, and the emerging future. So when I was preparing my talk, I crossed on Facebook with what we can call the paradigm of the pavement design, and that is something like this one. And we have a past characterized by solid roads made by person without the knowledge that we have at this moment. And in the present, we have roads that were designed with very sophisticated design programs and softwares. And after a long period, or sometimes a short period of time, we have potholes, and typical for the road materials, the road pavements that we have at this moment. And the question that we can put at this time on the table is, and what about the future? And this picture remembered me my presence in the farewell speech of Professor Molenar from TU Delft 10 years ago, where he did an excellent presentation and he presented the reasons for potholing. And he said that we need PhD. Yes, PhD, pothole doctor. So it's important to have a solid knowledge about all of these reasons for potholing, starting with traffic, climate condition, rain, temperature, materials quality and compactability, pavement design, construction quality, to avoid potholes and to construct solid and better road pavements. So let me start with the past. And for me, past is the period of time before 1962, when the first conference about pavement design was held in Ann Arbor, where the research defined principles for the Mechanistic-Empirical pavement design method and approach. So, before that conference, the pavement design was based on the empiricism. So, and the methods that we had at that time was the empirical method. So the past is characterized by these four steps. The first one, from the Roman and Macadam roads to the beginning of the 20th century, where we start using the asphalt pavement. And the past is also characterized by a lot of full-scale tests that were used to support the pavement design. And after that, we had the first design methods, and I'll show two of them. And the most important was the AASHTO guide for design of road pavement. So at the beginning of the last century, the design of the pavements was based on an empirical approach, and the thickness of road pavements range from 10 to 30 centimeters. At that time, it was considered that 20 to 25 centimeters was sufficient to protect the pavement foundation. And the pavement design was based on this principle. What is the thickness that we need to put on the pavement foundation to protect that foundation? At that time, at the beginning of last century, 20th century, the pavement the asphalt pavement were constructed with a very thin asphalt layer, range from 12 millimeters, is half an inch, up to 37 millimeters, that is 1.5 inch. This asphalt layer was only to protect the surface of the pavement and to provide functional quality of the pavement without any structural capacity. So that was the beginning of the science of the whole road pavement. And the first design method appeared at 1941 or 42, it depends what is the origin of the method, and was the CBR method that was based on or developed based on the pavement behavior from 1929 to 1941. It was firstly published by GUM, but the method that we know is from Porter, that added to the original method the curves for design for light and heavy traffic, and mainly for design of airport pavements. So that was the first method that we used during a lot of time, because despite its empirical approach, it was based on a lot of pavement observation, and you work not extremely perfect, but it was very good for that time. During the past, a lot of full-scale tests were carried out to support the pavement design. The most known method was the AASHTO road test that was the base for the design method. But let me talk about the wash road test, because it was one of the most important for the road engineering, because mainly during this full-scale test, the Benkel beam was defined, and it was used for more than 50 years for the analysis and the evaluation of the bearing capacity of road pavement. But one of the most important thing was the development of the first fatigue machine to evaluate fatigue resistance of asphalt mixes. And here at the middle of this picture, we can see the mechanism that they developed to simulate not a single axle, but a single and dual axle, and also to simulate the distance between the axle in a track. So it was an interesting approach to define the fatigue resistance of fault mix, and 10 years later was used to develop the mechanistic-empirical pavement design approach. But the most important one was the AASHTO test. It was constructed at middle of last century. It was constructed with 6 loops, one for climate condition, and you can see or you can find in Google Earth a photo of the loop 1 that was used for climate condition. This full-scale test was constructed with more than 400 trial sections. So these were sections with different compositions in terms of materials and thickness. So it was a very extensive trial sections. So they include also bridge. In the case for bridge, it was tested with more than 100 vehicles, and they travel more than 28 billion of kilometers. So, and the main concern at that time, and that was the objective of the AASHTO test, was the definition of relationship between the number of applications of a given axle of different values and configuration and the performance of different pavements. In this case, they test asphalt, pavement, plain concrete pavement, and reinforced pavement. And in this picture, you can see the trucks that they use to test the pavement, and they travel more than 20 million kilometers. So it is a huge test to validate a lot of different configurations for the pavement that they use at that time. And the most important result was the definition of a PSI, a pavement serviceability index, that defined the quality of a pavement based on the roughness, here defined by the SV parameter, the cracking, the patching, and the rutting. So the quality of the pavement was not defined in terms of the bearing capacity that is important for us as road pavement engineers, but on what the user feel when they travel on the pavement. And also they define the pavement behavior expressed in terms of the thickness index against the number of load application. And that was the base for definition of pavement design method. And after this test, they should define or develop the first design guide for the design of road pavement. The first version appeared in 1961, and we had different versions until 1993. And the payments present consideration about the main topics for payment design. Start with payment performance, traffic, foundation in terms of the characterization of the soil and how the soil is defined for design. the performance of the materials, environment, drainage, reliability, life cycle cost, and shoulder design. This topic, shoulder design, was considered in the previous full-scale test because the engineers at that time considered that the shoulder had an important influence on the behavior of the pavement by confining the pavement structure. So the most important equation from the AASHTO guide is the equation for design of the road pavement. That is this one that is based on or a function of the PSI, so is the quality of the pavement, mainly between difference between a initial and a final quality. The subgrade or the foundation modules and the thickness of all pavement. And another important parameter for design is the equivalence factors that relate the performance of a load to a reference load. And this guide define the axle load equivalence factor for flexible pavement, rigid pavement, for different type of axle and different type of structural number and pavement quality defined by PSA, or the difference between the final and the initial PSA. And an example here is here in this table at the right-hand side. But also another important achievement of this guide was the definition of procedures for economic evaluation or economic analysis of different alternatives for road payment. So when we design a payment, we must consider different alternatives, and they propose methods for the economic evaluation, and they include agency costs and user costs, and the analysis of all these costs can be used to define the best solution for payment design. So that was the past in 15 minutes. So about the past, we have a lot of things to talk, but probably not in 15 minutes. Let me go to the present, and the present is defined or is started in 1962, when the Mechanistic-Empirical approach was defined in Ann Arbor conference, with the main contribution from Shell researcher, Asphalt Institute, and the Road Research Laboratory from UK. So at that conference, they define the Mechanistic-Empirical approach based on the evaluation of fatigue cracking, and permanent deformation due to the pavement foundation. So the present start at that time. And if you compare the procedures that were used during the empirical period and the mechanistic-empirical period that we have at this moment, we can see that the approach is almost similar, or they are similar for the input, and the difference is the analysis. Because for the empirical approach, the analysis of the pavement performance was based on pavement observation of similar pavement in similar condition, while for the mechanistic empirical approach, the stress analysis was based on calculation of stress and strain in the pavement. And with this stress and strain, we define fatigue, permanent formation, and other distress resistance. So these two approaches are similar, except how we define the pavement performance. And in mechanistic empirical, we define it based on fatigue, permanent formation, and so on. So the main benefit of this mechanistic empirical approach is because we can use different loading conditions, different materials, and different distress modes for pavement design. So that was the main benefit of this approach. And based on this approach, a lot of design methods were developed, starting in 1963 by the design charts for flexible pavement developed by Shell. But we have also another important pavement design method started by the LCPC, this French one, Shell, Asphalt Institute, UK method, and the present we have the MEPDG. So let me talk a little bit about the Shell method, because it was one of the most important methods, probably the first one if you consider the design chart for flexible pavement. And after that, I'll talk a little bit about the MEPDG. So the Shell method, it was extremely important because it was used by a lot of people to define stiffness of the asphalt binder and the stiffness of the asphalt mix. So and here you have the monograms for the calculation of both stiffness. And the method, it's extremely easy to use because design criteria for fatigue is defined by a law that relates fatigue life based on the horizontal strain at the bottom of the asphalt layer, the binder content and stiffness of the asphalt mixes. And in terms of permanent formation, the permanent formation resistance is only based on the vertical strain at the top of the subgrade. So it was a very, very easy method to use in the pavement design. So, but at this moment we have the Mechanistic-Empirical Pavement Design Guide called MEPDG, that is a step forward in pavement design, because in terms of stresses, it considers not only the rating due to the subgrade and fatigue crack, but the method has more 5D stress, mainly the rating in granular layer, the rating in asphalt layer, longitudinal cracking, roughness, and non-related cracking. So it's a very complete method that includes a lot of distress for the pavement design. And compared to the previous one, is a step forward in the pavement analysis. And also important characteristic of this method is the incremental damage that they use based on a monthly analysis. So the pavement is analyzed by periods of 1 month during the entire period of life. The models were calibrated based on long-term pavement performance database, but can be calibrated by the use to adapt it for different countries, different states, and different conditions. Let me show how the main distress models look like in the MEPDG compared to the shell method. So this is the model for the permanent formation, and as you can see, you have extremely complex model with a lot of coefficients only to define the permanent formation. If you look for the shell one, is a model only with one parameter. Yeah, I have also here the fatigue crack and distress model, and you can see how complex is this model. And as an example for comparison, we have here at the bottom the shell equation for fatigue crack. That is very easy. So as we improve the pavement design models and quality of design, we are improving the complexity of the model. And here you have two examples, one for permanent formation and one for fatigue cracking. And in terms of comparison, we can see that for the MEPDG, we have 76 coefficients and 21 equations for flexible pavement that can be configured for different application. So the model is extremely flexible, so we can adapt it for any type of configuration or type of materials, because the model can be completely personalized for different material, different climate condition, and so on. But the most important is the results that the MEPDG present, because the analysis, it was based on a monthly process. So the results appear for each period, for each month, and it's good for the whole agency to define a policy for maintenance, because they can see how distress evolve during the payment life, and they can decide when it's important to carry out a maintenance procedure. But in present, we have also full-scale tests, and this is most of two important one from National Center of Asphalt Technology of Auburn University, and the most important one for me is from the Minnesota Department of Transportation, MN Road. That's where we can simulate real traffic and control traffic. And the real traffic is applied by the freeway, where we have three lanes, and we can cut one for maintenance and for testing. So it's very, very flexible, where we can do a lot of things. And they have also a loop for controlled traffic. In fact, they have two loops, one for heavy traffic and for agriculture, and another one for agricultural traffic. But we have, in present, we have also accelerated loading tests for those that are attending this my speech from ICT. You have accelerated loading facility, a linear one, but there are different configurations from circular and oval trucks. And here we have the most important for circular, that is the French one, and for Oval, probably this one from Spain is also one of the best or one of the most important. And these accelerated load facilities can apply loads up to 140 kilonewton and speeds up to 100 kilometers per hour and wander up to 350 millimeters. So here you can simulate all the conditions, and in most of them, for example, in the last one in this picture, we can see the Spanish one where they can apply climate conditions for on the pavement, simulating different temperature and rain and water and so on. So that is the present, and let me talk a little bit about the future. And when we think about the future, we can put on table these two questions. Did anyone predict the pandemic or the World War III? Probably no one, because it's not easy to predict future. That's why I'm calling the emerging future. So what I'll talk about the future is about the emerging future. What is happening at this moment in terms of future? And it's not easy to define what we will have in future. For example, in an idea competition for roads for the future for Paris in France, this company, Roger Strike, Arbor and Partners, define that, or they think that the future is something like this one. We have cars, probably different cars, not for 5 person, but only for 2 person, on a conventional payment, but probably the type of payment will be different. And you can see at the right-hand side that pavement is almost green, not with asphalt, but with cement concrete. The type of vehicles probably, or they look like a little bit different, probably autonomous vehicles. We have also a lot of green around the roads that change the behavior of them. So in terms of future, it's not easy to define what the future will be, but there are some people that try to think about that. One of them, this organization that is a forum of European National Highway Research Laboratory, that a couple of years ago, they define what will be the future, or probably will be the future. And they said that the future of the road payments or of roads will be based on these 2 ideas. So we will have adaptable roads that are roads that we can change to have different characteristics and different properties. Automate the roads, because the traffic will be automated in a couple of years, and resilient roads to be adapted or to adapt to the climate changes. But it's this idea, so I don't know what will be the future, and to talk about what the future will be, if you look for the current research trends, and I did it for these journals about road payment, road materials, and payment design, and for 2 most important, for the road materials pavement design journal and the International Journal of Pavement Engineering, I got the titles of the last 250 publications of each one, and produce a cloud of words, and and as you can see, they are doing almost the same. So the most important word is asphalt, pavement, probably performance, concrete, property. So it's based on the last research that was published in this journal. It's not easy to define what the future of payment will be. Or probably we'll have different approach for fatigue resistance analysis, and if you think about the linear viscoelastic continuous damage that was developed by Professor Richard Kim almost 25 years ago, and the number of publications about continuous damage at this moment is starting increasing. And before the 2010, the number was extremely low, no more than 5 per year. But at this moment, we have more than 25 publications per year. And last year, the total number in this journal, Road Material Pavement Design, International Journal of Pavement Engineering and Transportation Research, record the number of publications with this word, continuous damage, or viscoelastic continuous damage, reach 40. That is an interesting number. Probably the future, probably this analysis will be the future for the fatigue analysis of road materials. And that is amazing, because with this analysis we can convert viscoelastic problems in linear problem by defining the pseudo stiffness of the materials and the damage parameter, and if we and the evolution of this parameter, the damage and the pseudo stiffness, follow the trend that we have at our right-hand side. But if we plot the pseudo stiffness again the damage parameter, we can see that the line or the curve is the same for different sand level. So in this case, it's interesting because we reduce the testing time for the analysis of road materials. But probably one of the factors that will affect the payment that we know at this moment will be the connected and autonomous vehicle, called CAV, that are vehicles that connect to the other vehicles, to the infrastructure, and to everything, that probably will define a different way how we see the roads and how we see the pavements, how we design the road pavements. And at this moment, there is some large project in US and UK that are dealing or are trying to study CAV and how the roads will be changed by this traffic, and also the payment. And the number of publications about CAV are increasing at this moment. We reach almost 200 publications, mainly on emission travel time, effectiveness, but on road pavement, the number of publications at this moment is very reduced, and is limited to a subject that was included in MEPDG as the wonder by different strips where we have 20% of traffic, and at this moment there is a lot of research, not a lot of research, but some research on this topic for design of the pavement, and it's related with the transverse and the horizontal positioning of the vehicle during the circulation. So I was at the end of my speech. Hope you enjoy it, and thank you so much for your attention.
Thank you, Professor. Do you have any questions in the room?
Thank you, Professor, for the nice presentation. I noticed that you didn't mention in your slides any use of finite element method to predict pavement responses or even the stress resistance, because it's out of your area of expertise, maybe, or do you believe that it's not at a point where it could reliably be used for pavement design?
Well, okay, thank you for your question. It's an interesting question. So the objective of my talk is only to make a small overview of the pavement design, not to go deep on the pavement design. But if you remember the MEPDG, they use they use finite element modeling for rigid pavement, for example, and for flexible pavement, for example, the MEPDG don't use that approach. But if you look for the model developed by Richard Kim for linear viscoelastic continuous damage, then also based on finite element. So the finite elements then will be used, and they are important or very important on the pavement analysis and design, but it depends how we want to get the results. For example, for the typical pavement distress, for example, for the fatigue crack and permanent formation, probably you don't need to use that. But for example, for top-down cracking, because the crack is due to the shear effect on the edge of the tracks. In that case, it is very important. So the use of finite element will be important based on what we want to analyze. And for pavement design at this moment, we are using that tool for rigid pavement. For flexible pavement, then MEPDG don't use that because the MEPDG is also an empirical pavement design method, and they consider, for example, the top-down crack not by evaluating the shear stress at the edge of the tracks, but they combine it by the other stress and strain on pavement and correlate it with pavement observation. So, but it's important, and it will be used in future for sure.
Thank you.
Do we have other questions? We have a question on Zoom from Muhammad Kahali. He's asking, are artificial intelligence and machine learning going to be somehow integrated and utilized in the emerging future of pavement design?
Sorry, could you repeat a little bit slowly and more close to this microphone, please?
Are artificial intelligence and machine learning going to be somehow integrated and utilized in the emerging future of pavement design?
Yeah, for sure. Machine learning the other tools like that one will be used in payment design, mainly when because when we analyze a payment or we perform a payment design, when we increase the precision of the models, we need a lot of time for the calculation. And in that case, machine learning is a good tool to reduce the computational time for the analysis. So that will be a tools that will be applied in payment design in a couple of years, probably, for sure.
Thank you. We have another question in the room. Ahmed?
I have another small question, Professor. I was wondering what the pavement design code is in France. Do you use something similar to what we use here in the US, or is it they have like a different procedure?
Could
Okay,
you
never
repeat,
mind
please?
that. I thought you were from France.
Sorry.
Never mind, Professor. I had a mistake in my question.
So please repeat your question, because
I was wondering if the design procedure you used in Portugal is the same as the one used in the US, or is it something completely different over there?
Okay. Thank you so much. I'm sorry, because in Portugal and in other countries, this design at this moment is different with very strange procedure. Okay, so for example, in Portugal, we are using shell method. All people use the shell method because the shell is European, but different countries use different method. For example, the countries that speak French, they use the French approach. In Africa, the countries that talk English, they use the English method. So all methods are important, and we get interesting result or good result with all methods. And the countries define one method and they use each one without any problem. So in Portugal at this moment, we are using shell method. I don't know if we'll change the method to the MEPDG. Probably not, because the method is extremely expensive. So at this moment, the people don't need in Portugal. They don't need to pay for another method, because they have the shell method, and shell method only require the bizarre software for the calculation of stress and strain in payment, and they can use that stress strain and Excel spreadsheet to calculate fatigue and permanent formation resistance. So in Portugal we use shell method. Probably we don't change in a couple of years.
Thank you.
Thank you.